Yes, sir. We can start, sir.
Okay, all right. Welcome everyone to this live session for the NPTEL course Measure Theoretic Probability 1. In this course, we have been covering the basic mathematical foundations of probability through measure theoretic setup. Towards that direction, what we have focused on is the structure of sample space together with a sigma field, which will consist of all the special subsets or the events corresponding to certain random experiment of interest. And then finally, we also have a probability function or a probability measure that will associate certain physical significance, which will try to connect to how rarely or how frequently certain events occur. So there is a numerical quantification that is being associated by the underlying probability measure. So that constructs the domain side structure or the probability space structure. And then as a domain on that domain, we are looking at specific type of numerical functions, which we call as random variables, which need to satisfy certain condition called measurability. And what we have studied is that under that random variable, we can then look at the corresponding law of the random variable, which is on the real line, which appears to be a probability measure on the real line together with the Borel sigma field. And as long as you know that probability law or the probability measure, then you can write down the probability of any event of interest that connects to that random variable. So therefore, as long as you know the law, you can then afford to ignore the domain side probability space structure as long as you know that. This is very important. And then what we have also shown is that using that probability law, you can actually talk about integration structures. And then we have studied certain basic properties regarding measure theoretic integration, and they involve certain very fundamental results. And why these are important? Because we are able to define the expectation of a random variable in terms of the integration of the random variable with respect to the underlying probability measure. And then we can change the measure and connect it to integration over the real line, but with respect to the probability law. Okay. So that's how the expectation is defined for general random variables, no matter whether it's a discrete, absolutely continuous, or a mixture, or any other type of random variables. So this is defined in a very generalized setup. And then using all those fundamental theorems, we try to make some understanding about this integration or the expectation of random variables and also for higher moments. So toward the end of the course, we have also looked at certain fundamental inequalities that connect expectations or moments together with probabilities involving the random variable in terms of certain events. So those are what were the course contents. So what I would suggest is that you go through each and every result very carefully. Focus on the practice problems, the assignment questions. Now that you will also have the standard solutions available, so please practice them so that it will help you in understand the content better. And I am sure all of you who are taking part in that examination will do well. Okay, so please go through all the technical details, all the basic details, make sure that you understand, and then perform well in the examination. All right. So in today's discussion, in today's discussion, we'll start off with certain questions that has already been collected through the Google Form survey. So I will go through them one by one. And after that, if you are online, you are welcome to post your questions in the Zoom chat box if that is convenient to you. Or alternatively, you can go to the YouTube live session also. So there also you can post your questions. So we'll take them up. All right. So let's start with the questions that have been collected through the Google Forms already. All right. So I will read off one question at a time and try to explain the concepts. All right. So the first question is this. How does the Radon-Nikodym theorem justify the use of probability density functions? So let's start from the basics. So what we have said is that if you have any probability measure on the real line, then it will have a decomposition given that there is a very standard measure, which is the Lebesgue measure, which is the usual length function on the real line that is available to us. So you can take any general probability measure and compare it with the Lebesgue measure, the standard measure. Then you will have two specific pieces of the probability measure, and that's where what you get is there is a specific type of a decomposition already available. So there will be a kind of a continuous part available to you, and another will be a purely a jumped out. Now what is happening is that these decomposition also is available in terms of the underlying distribution function. So again, you can look at the corresponding decomposition in terms of the distribution function. So you will have a continuous part and you will have a jump part. And further, the continuous part splits further into the absolutely continuous part, and that there is a singular part. So that's how you end up with three types. And typically, a general random variable or the corresponding distribution function would be a convex combination of these three. A general random variable will be a mixture of these three taken together. But for our analysis, it's always good to work with one specific type at a time. And in the special case, when the entire probability measure is completely given by as under the absolute continuity condition with respect to the Lebesgue measure, then you can split it in terms of an integration with respect to the Lebesgue measure. And there, by the Radon-Nikodym theorem, tells us that you must have a specific type of a integrand that will appear in the description. So the general probability measure of an absolutely continuous random variable is therefore given in terms of integration with respect to the Lebesgue measure, but with a special type of an integrand. And that integrand is the probability density function, which is determined up to sets of measure 0 with respect to the Lebesgue measure. So we call it the because it's unique in that sense that you can change the possible values on a set of measure 0, but otherwise the values are kind of fixed. Okay, so you get a kind of a quote unquote unique function which appears as the integrand. And that's what we call as the probability density function. So that's how the Radon-Nikodym theorem allows us to get the probability density function provided the underlying random variable is absolutely continuous. All right. So I hope that clarifies the question. So let's go to the next question. It says, why is expectation of absolutely continuous random variables defined through integration? So the idea is not that you only need to work with absolutely continuous random variables, but what we are using is using the measured theoretic structure, defining the expectation of any general random variable through integration of the random variable x with respect to the underlying probability measure p. But as we use transformation rules, you can write it as an integration with respect to the underlying probability law. And for that part, using the underlying probability law, you can rewrite in terms of the integration with respect to the Lebesgue measure. You will need to bring in the probability density function, provided your random variable is absolutely continuous. And then this becomes a special case of the general definition. So if you are working with the absolutely continuous random variable, your underlying probability law is absolutely continuous with respect to the Lebesgue measure. So then the integration which gives you the expectation can be written in terms of the Lebesgue measure, but you have to now bring in the probability density function. So that's how for the special case of absolutely continuous random variables, you get as an integration with respect to the Lebesgue measure, but you need to therefore multiply whatever integrand you have with the probability density. So the general definition for any general random variable is defined through integration, and in the special case of absolutely continuous random variables, you get a simplified form. All right. And final another question is this: can you give an example where inequalities involving expectations provide useful bounds? So you see there are these standard bounds that are given in terms of the Markov and Chebyshev types inequalities. So just to take an example. So there, for example, in the Chebyshev type inequalities, what you try to do is that you say that my random variable x is away from the mean in a certain error, which will be, let's say, compared in terms of epsilon. then such a probability is dominated by variance divided by epsilon squared. So that's how the type of estimates you get. And therefore, for very large values of epsilon, you automatically get that the variance divided by epsilon squared, that type of a ratio is very small. So that tells you that the probability of the random variable moving very far from its mean, it's small. So that's how you get some nice estimates of the probability or in terms of the bounds that appear through this type of inequalities. So of course, if you are using some specific type of an epsilon, some specific value of epsilon, such that that ratio is actually greater than 1, then that is a trivial bound for probabilities and that does not provide any useful information. So you have to work with some special choices of epsilon only where the appropriate ratios actually become non-trivial, strictly less than 1, then that provide useful information. And if you take epsilons larger, then those ratios become smaller. And then is where you get more useful strict inequalities or special types of additional information that you get through these inequalities. All right. So I hope that clarifies that question. So let's move on. All right, so we get another question that in practical data analysis, we often deal with infinite sequences of random variables. Please give an example where applying the dominated convergence theorem help us justifying the exchange of limit and expectation. All right, so strictly speaking, the dominated convergence theorem is very useful in computing expectations in complicated setup where the limit random variable is hard to work with, then you use some nice smoother approximation. So that's how typically things go. And typically what will happen is that in many types of examples, you would finally write it in terms of integration with respect to the Lebesgue measure. And if the integrand is very complicated, you get some nice approximation for which it's easier to compute the integration. And then you try to justify the limit. And that's where the dominated convergence theorem comes in. And just to give you a preview, actually in this specific course, we have not really talked about convergences or random variables, but later on there are follow-up advanced topics that you can read where you need to look with convergences of random variables, and that's where the dominated convergence theorem plays a very significant role. It actually says that if you have nice convergences available point-wise in the almost sure sense, then you can talk about moment convergences or convergence in moments, and that comes as an application of the dominated convergence theorem, provided you have the appropriate bounds available. All right, so right now is not the correct place to talk about the full importance of the dominated convergence theorem, but I hope you got the idea. So I would also suggest that you look at the worked out examples in the notes, exercises, as well as some of the books that has been referred to. You will find other applications of dominated convergence theorem related calculations there. All right, so let's move on. So then there is this question that what is the importance of monotone class theorem in probability? All right, so let's try to understand where exactly we have used the monotone class theorem. The monotone class theorem was actually used in the characteristic extension theorem to talk about the uniqueness of the probability measure. So in the specific setting of probability, specifically focus on the real life where we use real valued random variables in that setup, then we have to understand the probability law, which is a probability measure on the real life. Now, to understand that probability law, what the characteristic extension theorem is saying is that it's good enough if you can understand the probabilities on special types of sets which come from a field that generates the Borel sigma field. Remember that we have talked about this left open right closed intervals and their finite disjoint unions. They form a field. And that field also generates the Borel sigma field on the real life. So using the characteristic extension theorem, the uniqueness part that comes from the monotone class theorem, that will actually tell us that the probability measure is as long as we understand it on this finite disjoint union of left open right closed intervals, we are done. All right. And then we have discussed this in the notes. please go back and check, is that therefore, since you need to understand it's on those type of sets, the finite disjoint union of left up and right closed intervals, using the finite additivity property, you can as well try to understand it on any fixed but arbitrary type of left up and right closed interval. And that again can be further relaxed to intervals of the type minus infinity to x closed. So if you can understand the probabilities on this type of intervals, then that's good enough. But that exactly gives you the distribution function of the underlying probability measure or the connected random variable, right? So therefore, the idea is that the law of a random variable is essentially getting determined through the distribution function. So if you know the distribution function, then it's uniquely determining the law of the random variable. So we also said it in different way that if you have two random variables and their distribution functions match, then the random variables are identically distributed, right? So they have the same law. This is where the Morton class theorem comes in. This gives you the uniqueness in the catastrophic extension theorem, and that allows us to connect the probability law of a random variable through its distribution function. And that identification is one-to-one. That comes from the uniqueness of the catastrophic extension theorem, and which essentially follows from the monotone class theorem. So I hope that you understood this clarification. All right, so there are no further questions. So I would now go to the Zoom session. So no further questions have also been posted in the chat box. All right, so also let us check the YouTube live session. So far there are no questions in the chat box here. So if you have already joined in, please feel free to post your questions or doubts in the chat box. We can wait a couple of minutes. So if you are online, please post your questions or queries or any other comments in the chat box. Okay, so there does not seem to be any follow-up questions. So let's we can wrap up the session today. So best wishes to all of you if you are registering for the course examination. So I hope all of you perform well. And those of you who have just decided to continue with the course to learn the material, so I hope that it has helped you understand the concepts. And if you have any queries, you are welcome to post your questions in the Google forum. So we'll hope to respond there and have interactive discussions there. All right. So we are closing off the session today. Thank you for your attendance in the course and best wishes again. So goodbye for now.
Thank you so much, sir, for your valuable time. We will close the session, sir.
Yes, yes. Thank you. Thank you.
Okay,
All
sir.
right. Okay.
Yes.
Goodbye. Goodbye. Bye.
Bye, sir. Thank you, sir. Yes, sir. I stopped the streaming, sir.
Okay. So I'll